Hello students, welcome back. Let's go to problem 2. This time we're going to study means, not proportion anymore. In 1995, Cook County, Illinois conducted a study to determine how far the head of household traveled to work. A simple random sample of 2,518 households was chosen and the occupants were interviewed. The survey found that the mean commuting time for a head of household was 42.6 minutes and the standard deviation was 16.7 minutes. Thus, the study suggests that the true average commute time for Cook County, Illinois in 1995 exceeded 42 minutes. I got this problem from one of the textbooks I consulted, so I assume all these figures here are correct and actual study took place. Okay, let's set up the hypothesis. So mean commute time of head of household is approximately equal to which minutes? How many minutes? We have two candidates here. Which is it? Again, the same question. For null hypothesis, we want something is equal to whatever minute. Now, which one came from sample? Which one did not come from the sample? Which one came from the average of the interview for 2,518 households? And which one is just dropped to you by this problem? Read carefully, and this one, and also along with the standard deviation, they came from the sample. You see, the survey found blah blah blah, so they both came from survey. So they came from sample. Now this one, this did not come from sample, so that's gonna be the null hypothesis. An alternative, either greater or less. Sometimes not equal, but that's really rare, and I don't think I'm gonna ever consider that kind of thing. So either greater or less, and we have 42.6 minutes, so probably we are thinking about greater. And also, keyword exceeds 42 minutes, so it's got to be greater. Okay, we are done with the hypotheses, and remember how to set up null hypothesis. The number associated sample, that's not it. That's something we use in the solution. To set up the hypothesis, you have to go with the other one. Okay, all right, let's test the hypotheses. As before, we're going to talk about critical value method first. So draw the normal picture around 42 minutes, and that's natural to you because after all that's null, and then find out the critical value to the right. Well, sample size is really large, so clearly this is a z-test problem, not t problem, and hypothesis, all right. And sample statistics, I have to run this in order to get the graphing programs here work properly. So mean is expected to be 42 minutes, approximately speaking. As a matter of fact, it's not really correct. That's something we are testing, so it's not just equality period. It should be question mark. And then that's what we found. Sample mean is 42.6. What is this? I don't know what I did there. I must have missed something. Okay, maybe just a typo, I guess. All right. Here in mathematical command, everything looks okay. All right, here's the initial picture. You can hand draw this picture, go the outline, and the center is always a null, and then where do you put the end? The end is a critical value. So you don't know that yet. Okay, here we go. 42, and end is a critical value you want to find out. And that's associated to, let's see, 0.05, so 5% here. Again, the same alpha value, same z-score. Make sense? That is the critical value approach. Find out this critical value once that is done, and then we can compare that with the observed mean. The observed mean of 42.6 minutes may fall in blue region, okay, then close enough to null, so null wins. May fall in the red region, too far away, so alternative wins, null loses. Let's figure out this critical value x. Standard deal, n minus center over SE. By this time, everybody should be absolutely comfortable with this z-score formula, n minus center over SE. And then, as we found out before, you have 5%, so 1.645. Let's go to the z table again. Let's go to 5%. Yeah, okay, right here. 0505 or 0495, and that's associated to negative 1.645. And this is to the right again, so positive 1.645, just by symmetry. And then solving for this x, again, flip this to the other side, multiply, and then flip that to the other side by adding up. And this is a computation we have, and here's the result, 42.54 something. Whew, very close to 42.6, but 42.6 is clearly greater than that critical value. Graph will tell you everything. So here's the threshold, critical value, 42.5474 minutes, and 42.6 minutes is clearly greater, it's too far away from the null, it falls in the red region, so HA wins. The critical value approach has this z-score computation, and then you have to find out the end, something we have been doing all the time. And once you get that, then it's easy to understand. Where does the observed mean fall? Close to null or too far away? You can clearly see it. If you have appropriate shading, you can really clearly see it. And if you have some, what do you call, highlighters, things like those, then you can use two different colors like this, blue, red, or I don't know, some other colors, yellow and purple or whatever, and you'll be able to visualize really well. So, relatively easy to understand. You can use probability value method as well if you want to. Hypothesis, of course, remains the same. And the sample statistics, again, all the same. I just copied and pasted incorrectly. 42.6 minutes. Yeah, it's correct here. It's running correctly there. And then initial picture is a little bit different. We're not looking for the critical value. Oh, wow, I have... okay, don't pay attention to this coding here. You're not going to be a programmer. Okay, never mind about that. Okay, all right. Actually, you know what? Significant coding program is actually hidden here. Okay, in computer science point of view, this is not significant, but still, there's some coding there, and you're not really interested in programming. Just look at the picture. This is null, and this is a critical value. This is the observed value, not the critical value. Now you're looking for the p-value here, the probability that will exceed or at least equal to the observed proportion, observed mean, excuse me, this time. And that is called probability or p-value. And then here's the hard part. And then what? We can calculate the z-score and then look up the z-table and find out this p-value. Great. And then what? P is greater than alpha, then P is less than alpha, then that's the hard part. So my suggestion is try not to use this. Try not to fall in love with this unless you know what you're doing, unless you do understand the concept of that type 1 error and the conditional probability concept. If I tell you the conclusion, P is bigger than alpha, then null wins. And vice versa, P is small, then alternative wins. Let's find out. Z-score, n minus center over SC, and this computation is pretty much straightforward. And then once you get 1.8 something, all right. Look at 1.8 something from your z table, excuse me, should be z. And then 1.80 from your z table, 1.80, 0.9641. That's the probability, but then again, that's not what you're looking for. It's the other. 1 minus 0.9641 is the one you want, and if you do that, you're going to get this score. 0.035 something. And you can see that this is less than 5%, less than 0.05. Therefore, it's the alternative hypothesis. Alternative wins. What do I have here? I must have some... Yeah, okay, all right. I corrected the program, so now it's working fine. Okay, so the probability we calculated is 0.0357 and so on, and this is what Mathematica calculated, and this is what we got from z-table. Either way, it's kind of similar, and in any case, you can see that this p-value is less than alpha. So alternative wins. Reject null and accept alternative hypothesis. Now, if you're comfortable with this p-value method, go ahead and use it. We have enough time, so let's talk about hybrid method. And it kind of goes like this. It's a similar idea, except that instead of getting the normal table, or excuse me, the normal picture around the null hypothesis, make a standard normal and then draw it around 0. And then get, this is about going greater, so get z critical score for the right. And again, why right, why not left? Again, there's something to think about actually. And then we have to find out z-score, and then z-score for observed mean, and then compare those two z-scores. It's not direct comparison between the critical value and then observed mean. They're both processed, so it's a little bit more indirect, so a little bit difficult to understand, I have to admit, and that's why I see some more mistakes from the student who follow this method. In any case, here's a computation. You get the z-score from the observed mean and then get 1.80 something, and then you get should be z. You get z-score, z critical score from alpha value of 0.05, and can then compare these two. And then this one is greater, therefore what? Okay, there's another hard part. So in the end, yeah, it's greater, so alternative wins like this. Graphically, you can express kind of like that. Let's go back to method number 1. If you follow this, it's relatively easy to understand, and you don't really have much to worry about. You get the critical value through z-table computation. Once you put it in a normal picture centered at the null, then it's pretty clear where that observed mean x-bar is falling. Close to null or far away. It's crystal clear once you get this picture, so students do not make conceptual mistake here. The other method, a little bit easier computation arguably, but in the concept part, students make a lot of mistakes, and therefore I'm not really recommending those methods, to tell the truth.